Good evening, everyone. I'm Professor Andres Velendowski. I'm head of School of Mathematics and Physics here in the University of Lincoln. Very warm welcome, everyone who came to our 5th annual Robert Grosseteste Lecture in Astrophysics. Before lecture starts, I will say a few words about our university and our school, which organizes these public lectures, because many of you might come for the first time in this virtual environment and might not visit Lincoln before or might not visit university before. And so just a few words about our school and about our university, which organizes this series of public lectures. Good evening, everyone. I'm Professor Andres Velendowski, head of School of Mathematics and Physics at the University of Lincoln. And I will just say a few words about the university and the school, which organizes various public lectures. Traditionally, you would come to our public lectures in the evening to our beautiful campus by the waterfront of Brayford Pool. When you will come to Lincoln one day, hopefully maybe next year in person, you also will enjoy seeing the city, which is a small city of about 100,000 inhabitants, however with very long history. It was found by Romans very soon since they came to British Isles. It was once the base of famous Legion Number 9, Hispania, and received the prestigious status of Colonia and became Lindum Colonia, already in times of Emperor Domitian. Lincoln is a short of Lindum Colonia. If you walk in the center of Lincoln, you still can enjoy seeing some Roman remains, as this arch of one of survived Roman gates. The only Roman gate in Britain through which traffic still allowed. Next big step in development of Lincoln came with another visitors, with William the Conqueror. Soon after taking British Isles, he ordered to build Lincoln Castle, noticing the same spot as Romans found before. And soon after, there was order to build a cathedral, which started already in the 11th century. This cathedral is one of the most beautiful cathedrals basically on earth. In fact, for quite a few years, that was the tallest building on the planet. Then a central spire was in place before it was blown away by a very strong wind. Cathedral, of course, always have books. There is a medieval Lincoln Cathedral library. And when you visit a cathedral and will look on books on exposition, you might notice there is a note that one of books was borrowed to University of Cambridge a couple of centuries ago and still didn't come back. As cathedral was always place of learning very early in the days. And one name which is very special, in particular for this lecture, is Bishop Robert Grosseteste, who some think was the first English scientist. Definitely what he was writing and his writing survived nowadays belong to the field of physics and cosmology. And for that reason, we name our public lecture in astrophysics after Bishop Robert Grosseteste. While cathedral was here and there were various elements of learning. There was no university till 20th century. Then at the end of 20th century, the campus was opened by Brayford Pool by Her Majesty the Queen. And already in 21st century, university opened various schools in sciences. In particular, our School of Mathematics and Physics was opened in 2014, with first students arriving in 2015. From April 2017, exactly 4 years ago, we have our own building named after Isaac Newton, who also was from Lincolnshire. One day, when you will come to listen to our public lectures in person, they hold in this magnificent building in Isaac Newton Lecture Theatre. The university's main direction is advancing education. So I just list what our school provides to educate further generations of experts. We offer a bachelor and integrated master's degree, both in physics and mathematics. We have various joint degree, for instance, mathematics with philosophy or physics with philosophy. We have joint degree of mathematics and physics and mathematics computer science. Our physics degree have a substantial astrophysics component, and which is reflected also by the fact that our speaker tonight is Professor Don Kurtz, who is also a visiting professor of our school. And with that, I welcome everyone to our 5th Annual Robert Grosseteste Lecture in Astrophysics. Hello, everyone. I'm very pleased here to have our speaker tonight, Professor Don Kurtz, who physically talking to us from South Africa. Before Don will start his lecture, I'll just mention that you can put questions after the talk or during the talk in a live chat on YouTube. Or if you would like to have it completely anonymously, you can use Padlet, and the link to Padlet was in your email, and it also just appears in a live chat of YouTube as well. And now I will just say a few words about our distinguished speaker tonight, Professor Don Kurtz. Don comes originally from San Diego in California, and he also started his education there as well, obtaining a degree from San Diego State University in 1970, and then a PhD from University of Texas in Austin in 1976. After that, he went for just 1 year to University of Cape Town in South Africa, but that 1 year lasted basically 24 years. Then Don continued there and also became a professor and life fellow of University of Cape Town in South Africa. He also spent time in France in 2000, and from 2001 till 2020, Don worked in the United Kingdom in University of Central Lancashire in Preston. And in fact, I was fortunate to be a colleague of Don for exactly 10 years. Then I was working in University of Central Lancashire in Preston before moving to Lincoln. From 2020, Don holds the status of Professor Emeritus of University of Central Lancashire in Preston, and also he became an extraordinary professor of Northwest University in South Africa, where he is residing right now. Also from 2020, Don has a visiting professorship in University of Lincoln, in our school, and we are very fortunate to have Don with us. Don served in his long career in astrophysics in UK as Vice President of a Royal Astronomical Society. And sat on various committees, which I don't have all time here to mention. I only mention that Don is prolific public speaker. He gives dozens of talks every single year all over the world. And tonight, Don is with us in this virtual environment, which we all will be enjoying.
Thank you, Andre. Have you turned that over to me?
Yes, floor is yours.
Okay, thank you very much. Good evening, everyone. Or good evening if you're in the UK. If you happen to be watching this from somewhere else in the world, well then, good day to you wherever you are, or good night to you. I gave a talk a few years ago to a farmers club in a county in the UK, which I won't name. And it had a membership of only 12. A new member to join the club had to wait till an old member died. At the end of my talk, one of the farmers said to me, "What good is astronomy?" Now, that's a question we astronomers get sometimes. It sometimes comes from politicians. And when it's said in that tone of voice, the question really means, well, how can we make money out of it? What financial gain could come from astronomy? And there are many good answers to that. All of you have got phones now. Your phones run on GPS, and your global positioning system runs off the mathematics and the physics that was just maths and physics when I was a boy. We didn't have satellites orbiting the Earth. The detectors in your phone, which produced the camera, developed out of astronomical instrumentation that we astronomers developed to look at the sky better. There are many answers to that. But the answer I gave to this farmer was, you should just fund all of science, have all scientists go out, study the universe, study everything, and just try to find out how things work. Because from some direction that you don't see coming, some discoveries will be made that have got very handsome payoffs of the kind you're looking for. You just don't know where they're coming from beforehand. And one of the farmers, the one in fact who had asked the question, looked at me, he says, "Oh yes, I understand that. I understand that completely. My wife has 25 racehorses and you never know which one's going to be a winner." Well, that gave me thought. I think racehorses cost about £20,000 a year to run one. And if you've got 25 of them, that's a pretty impressive hobby. Now, I'm in the process now of uploading your talk right now, or this evening, and we will talk about the value of astronomy and the value of science. I'm going to tell you a story spanning approximately 400 years, although we'll go back further, of the greatest payoff that will ever come financially from any discovery in science. By the way, this is the last you're going to see of me until the question time. And so this is what I look like. And I'm going to disappear and just be a voice now as the slideshow comes up on the screen. I called the talk "The Stars Are Ours." That's actually a title I pinched from a science fiction novel I read when I was a little boy back in the 1950s. And it seemed to fit the talk for tonight. Now, speaking of payoff in science, here's a man whom some of you will know, maybe not everybody. I gave this talk last year in Australia just before the pandemic started, and the Australians all know this man because he is Australian. He's a national hero there. Howard Florey was an Australian scientist who worked with penicillin. Now, you know that Alexander Fleming discovered penicillin, but Florey and his team are the ones who turned penicillin into a medicine and provided us with antibiotics to save lives. It's estimated that the work that Florey did with his team resulted in perhaps 200 million saved lives. Now, I think everybody would agree that's an incredible scientific payoff. He got the Nobel Prize along with Alexander Fleming and Ernst Chain for that. And when asked later about the research, Florey had these words. He said, "People sometimes think that I and the others worked on penicillin because we were interested in suffering humanity. I don't think it ever crossed our minds about suffering humanity. This was an interesting scientific exercise, and because it was of some use in medicine, very gratifying, but this was not the reason that we started working on it." It's a beautiful example of somebody doing what he considered to be blue skies research, which had stupendous impact on all of our lives. There's a beautiful star cluster in the southern hemisphere. It's on the poster if you looked at that when you signed up for this talk. It's a very young cluster of stars. It contains some of the most massive stars known. Many of these stars in this picture you're looking at have lifetimes of only a couple of million years, and then they will explode as supernovae and die young. We humans, probably since the time humans became conscious, have looked up at the sky and we've wondered, what are the stars? That's a big puzzle, and tonight's story is going to be the answer to that. What are the stars? How did we come to understand them? And how did we gain control over the power of the stars? Our story begins on the 24th of May, 1543, in a cold stone tower in the fortified walls of a town called Frauenburg in what was then East Prussia, now is in Poland, not too far from modern-day Gdansk. In the bedroom of that tower, a man had lived for 30 years. He was lying on his bed, age 70, dying of a brain hemorrhage. He was in a delirium, not really aware of his surroundings, when his assistant walked into the room, brought to his bed and put down on the bed next to him the publication of his life's work. It had only just been published after 30 years' work on it. His name was Mikołaj Kopernik. We know him by his Latinized name, Nicholas Copernicus. On the left of your picture there, you'll see a modern-day picture at the museum to him of the tower that he lived in. His bedroom was on the second floor there. You'll notice a lack of windows. And this is a beautiful picture taken in the summertime. There, far in the north of Poland, much of the year, that's very dark, gray, cold, and wet. Copernicus brought back to human thought the idea that the sun is at the center of the solar system. Now, I say brought back because that was an idea the Greeks had 600 BC. They had a model where the sun was the center of the solar system and the planets orbited the sun. But the greatest authority of antiquity, Aristotle, said, well, if that's true, then as the Earth goes around the sun from side to side, we should see the stars wiggle back and forth because of parallax. And you can see that for yourself. If you hold your finger up in front of your face, blink your eyes back and forth, you'll see your finger jump from one side to the other as you see it in one direction with your right eye and then another direction with your left eye. And so Aristotle was being completely scientific. If the Earth goes around the sun, we should see parallax of the stars. We should see them wiggle. We don't, therefore the Earth doesn't go around the sun. That killed astrophysics and much of physics and science for 2,000 years. That pronouncement and the belief that that was correct. We'll come back to the parallax later, but Copernicus' great claim to fame is he put the sun back at the center of the solar system. In his one book, the book that was put on his bed, and he never was aware that it was there as he lay dying from this brain hemorrhage at age 70, called De Revolutionibus Orbium Celestium, or On the Revolutions of the Heavenly Spheres. Now, in that book, Copernicus also put the solar system to scale. But Copernicus was a rather reserved man. He was quiet, he was secretive, and it's often thought that he's perhaps the least colorful person who has ever shaped the direction of history. He overlapped with amazingly brilliant people who had a great impact on history but were flamboyant. Henry VIII, Charles V, Suleiman the Magnificent, the Borgias, Leonardo, Michelangelo, Albrecht Dürer, just fantastic people of a real flowering of human thought in arts and sciences. But Copernicus was withdrawn, not well known outside of scientific circles in his day. but he's the one who started the revolution we're talking about today. He determined the scale of the solar system in the following way. This is a schematic showing the inner part of the solar system. This is supposed to be the sun and the orbits of Mercury, Venus, and the Earth. We're approximating them as circles. We'll see in a moment that's not quite true. And the distance from the Earth to the sun is not known at the time of Copernicus. We didn't know how far away the sun was. We didn't know what the sun was. We call that distance an astronomical unit. I'll abbreviate that often as AU for astronomical unit. Now, at the moment, Mercury and Venus are much too close to the sun to see, so you're not seeing them now either in the morning or evening sky. But over a period of time, Venus can get at a maximum 47 degrees away from the sun. Mercury, with its smaller orbit, can get at a maximum 23 degrees away from the sun, and Copernicus was able to measure that. And then using trigonometry, he knew that the function we call the sine of this 47-degree angle was the length of this side, the distance Venus is from the sun, compared to how far the Earth is from the sun. And he calculated that Venus is 0.72 AU from the sun. He likewise calculated Mercury's 0.38 AU from the sun. He had to be a little bit more clever with the outer planets, but through some clever geometry, he could do it for them too. And if you look here, you can see that now in the early 1500s, Copernicus had these distances for the planets in terms of the Earth's distance to the sun, which was not known. And here are the modern values. And out to Mars, it's stunningly good. Not bad for Jupiter. It goes off a little bit for Saturn, but that's because Saturn's so far from the sun and takes so long to orbit, but still very good. At the time of Copernicus, we actually had a scale model of the solar system, but we didn't know how far away the sun is. We didn't know what it was. And so that's as far as it could go with Copernicus. Well, following Copernicus, our next character is perhaps the most colorful character in all of astronomy. He's a Dane who was born Tycho Brahe. We Latinized his name to Tycho, and then we anglicized that usually and just called him Tycho. Tycho was born 1546, 3 years after Copernicus died, and he was born into great wealth in Denmark. His father, Otto Brahe, was the governor of Helsingborg Castle. His mother, Beata Billa, was of nobility. She was a lady-in-waiting to the queen and also very wealthy family. Otto's brother, Jorn, was a vice admiral in the Danish Navy, and Jorn's wife, Inga, and Jorn could have no children. And so the brothers came to an agreement. The governor, Otto, and his wife, Beata, agreed that their second son, when he was born, would be given to Jorn and Inga to raise as their own son. And as luck would have it, the very first children that Otto and Beata had were twin boys, and Tycho was the second born. The firstborn died even before he was christened, and of course, the parents would not give the boy up. This almost led to a duel between the two brothers. There was a lot of bad feeling, but saner people got them to calm down and relax, and they made up with each other, and the topic was dropped until the governor and his wife had a second son, and then Jorn simply sent some of his Navy henchmen and kidnapped Tycho to raise him as his own son. Again, the brothers almost came to fighting over it, but they settled down. Otto and Beata, realizing that Tycho would inherit from Jorn his entire estates, would be raised well, and the family was happy that. So Tycho was raised by his uncle and his uncle's wife. When Tycho was a teenager, the uncle had won a great sea battle with the Norwegians, and he and the king apparently were drinking until they were both completely drunk, and crossing a bridge near Elsinore, the king's castle, the king fell into the sea. Tycho's uncle jumped in and saved the king's life, got himself out too, but caught pneumonia and died of pneumonia. And the king was very favorably disposed towards Tycho following that, and Tycho was highly favored. Now, that king was named Frederick II, and I trust all of you are familiar with the kings of Denmark over several hundred years, and you can name them for me. And if the answer is no, then let me help you. The kings of Denmark for hundreds of years were Frederick, Christian, Frederick, Christian, Frederick, Christian, Frederick, and so on. Frederick II was a patron of Tycho, paid him very highly, and gave Tycho enough money to actually found his own observatory and build himself a castle. Tycho had gone off to Europe to study in Germany. He was an outstanding student, and he saw a supernova explode. We know it as Tycho's supernova. He saw an eclipse of the sun, and he was stunned that it could be predicted, but he was not very happy that it was off by a day, and he thought that better measurements could get better predictions for things like eclipses. And so he was captivated by astronomy. His uncle wanted him to be a lawyer, train in law, which he did, and then come back and be a ruler of a castle, as the aristocracy were supposed to be. But Tycho had his heart set on being a scientist, and the family went along with that. In Germany, at the age of 20, Tycho got into a duel with another boy at a party at his professor's house. And you can easily guess right now what two 20-year-old boys get in a fight over. Who's the best mathematician? Tycho lost the duel, but he didn't lose his life. He ended up with a big scar on his forehead, and you can't see it in this picture well, but he lost the bridge of his nose. The center bit of his nose here was cut out. And for the rest of his life, Tycho wore gold and silver, and we now know, actually most of the time, brass prosthetic nose pieces to cover up the big gap in his nose. Now, the artist of this picture is not very good. I can assure you, if you look closely, Tycho did not really have two left hands. This is not very good on the artist's part to have got his hand around here backwards. But he became famous in his lifetime in Europe. He was a celebrity. Now, notice Tycho was born in 1546. 18 years later, 1564, was born the most famous Englishman of all time. And his name has immediately jumped to mind for you. 1564 was born William Shakespeare. 1599 to 1601, right at the end of Tycho's life, William Shakespeare was writing a play about a Danish nobleman, Hamlet. And he didn't have access to a Copenhagen telephone directory or anything like that to get Danish names. And it's pretty clear from this picture you're looking at that Shakespeare was aware of this picture. He was aware of Tycho, because if you look closely, these are Tycho's ancestors' coats of arms here. And there's Rosencrantz and Guildenstern, which became Rosencrantz and Guildenstern, of course, the two courtiers from Hamlet. So Tycho spent decades at his observatory, which was built on an island called Havane, which is right off the coast of Copenhagen, but is now Swedish territory. He built a palace in the new Palladian style, new at that time. You can see these formal French-style gardens here, the big palace, the gatehouses, and the gardens around it. He built a separate observatory because it turned out that the floor in the castle was not stable enough for his instruments. And he got all of the income off of all the people, the farmers who lived on this island. He immediately raised their taxes. He conscripted them to work on his castle. And he was not well thought of by the peasants who lived on his land. He abused them. He overtaxed them. It was a problem through his life. It's even said that he occasionally would have families completely kept in chains in the dungeon of his castle because of their failure either to work for him or to pay his taxes. He was a great party giver, and he had a pet that he kept under the table and threw scraps to at the parties. Pet's name was Jep, but the pet was not a dog. The pet was a human dwarf. And so Tycho was a privileged man growing up extremely wealthy. At one point under Frederick's rule, Tycho was receiving as pay or in support of his scientific activities 1% of the royal purse every year. He was the highest paid person in all of Denmark. The telescope had not been invented at the time of Tycho. He didn't have an optical telescope to look through. He had sighting devices. And here's a schematic diagram showing a great quadrant, which he could sight along to measure the positions of stars and planets in the sky, how high they are and how far around the horizon they are. We call that altitude and azimuth. Here, the artist is showing Tycho pointing towards the heavens. Here are a couple of assistants. If you look carefully, it looks like a dog lying here. But if your screen's good enough, if you look at the face of the dog, it's the face of a human. And this is probably representing Jep, his pet. Tycho could measure the positions of the stars and planets to 1 minute of arc. That's 1/30th the diameter of the moon. Far higher precision than anybody had ever done before. And he expected that measuring the positions of the planets, discovering their motion, would allow him to discover the answer to life, the universe, and everything, to be the most famous person who ever lived. He didn't agree with Copernicus. Tycho didn't believe that the sun was at the center of the solar system. He accepted that Mercury and Venus orbit the sun, but then he argued that the sun orbited the Earth. And we know now, of course, that wasn't true. He wanted to try to prove that with his observations. But then Frederick II died. Now, Tycho was married, but it was a morganatic marriage. He married a common woman, and according to law in Denmark, he could not marry her as he would an aristocrat, and his wife and his children could not inherit anything of his estate, and essentially the aristocracy didn't recognize his marriage. He was very happy in his marriage. They stayed together his whole life, but they were not well treated socially. And when Frederick died, Frederick had promised Tycho that his children would inherit his estate, but the new king was Christian IV. Christian was only 11 years old when his father died. There was a regency until Christian turned 16. And when Christian turned 16, he was not very favorably disposed towards Tycho and some of the other aristocracy. He thought they had too much power. And he didn't like the way Tycho was abusing the people on his land. And so he cut Tycho's salary substantially. I think you all are aware that no matter how much anyone has, if you take a little bit away from them, you can make them unhappy. And excellent example of that, maybe some of you in the audience are included in this, I don't know, but the bankers in London who take millions of pounds in bonuses every summer, take away their bonuses, they're very unhappy, even though they're still making millions of pounds every year. So Tycho's salary was reduced. He was unhappy. He looked for another position, found something in Germany, and then he landed the position as imperial mathematician to the Holy Roman Emperor in Prague. And so just to put it in perspective in this map of Europe and Scandinavia, there's Hvain off of Denmark here in Northern Europe. Here's Gdansk, where Copernicus was. And Tycho made his way overland, first to work in Germany and then to Prague, capital of the Holy Roman Empire, to work for Rudolph II. Rudolph was a character. He collected oddities, he collected art, he collected people. And Tycho was one of the oddities of humans that he collected and brought to him. Now, much of his great art collection was later sacked by the Swedes in war. It dispersed around the world. Some of it made it back into European art collections. And one of the paintings that I'm rather fond of is by an Italian painter named Arcimboldo. Rudolph liked Arcimboldo very much. That painting is now in the Art Museum in Vienna. And here is Arcimboldo's rendition of Rudolph II. And Rudolph liked this painting. He liked oddities. So Tycho came to Prague. He built an observatory outside of the town where he could continue his observations. He had to do horoscopes for the emperor, for his entourage. He had other public duties, and he needed help. And so he needed an assistant who could reduce his observations and do the calculations in order to make his famous discoveries and become, he hoped, the most famous discoverer of all time. That person he got as an assistant couldn't have been more different from Tycho. His name was Johannes Kepler. Johannes Kepler was German. He was born into a family of modest means at best. His father was a mercenary soldier who would go away to war, return, go away, return. Each time the family would have one more child. And finally, Father Kepler went away and simply didn't come back, and nobody knows what happened to him. We don't know if he died in a war, had another family somewhere else, and just stayed with them. So Kepler then grew up with a single mother with lots of children. Kepler was sickly from the time he was a child. He was a hypochondriac, but he had some real complaints too, which bothered him his entire life. He didn't get along well with Tycho. They argued, they split, they came back together. Tycho needed Kepler. He was a brilliant mathematician, but Tycho didn't want Kepler to make the discovery and become the famous person. And so he gave Kepler the hardest planet to work on, which turned out to be Mars. The reason for that, as we'll see, is that Mars has got a very eccentric orbit. I'll explain that in a few minutes. So he wanted Kepler to get the calculations done, but not make the discovery himself. Now, as luck would have it, Kepler was only with him for the best part of a year. And Tycho one evening was at a party at a baron's house in Prague, dining well, drinking well. He was a big eater and big drinker. He was a big man. And as you know, in Central Europe, they drink beer in huge, gigantic beer mugs. And he had had many of those, and he really did need to get up and leave the table. But he said he thought that that would be bad etiquette, given that his host was speaking. He had the willpower to hold it, and he burst his own bladder. It took him many days to die of it. He died in great pain and in delirium, repeating over and over, "Let me not seem to have lived in vain." He didn't live in vain. Kepler inherited those observations, and with them, with a period of nearly 20 years' work, Kepler discovered his famous laws. Now, I'm going to show you those laws in just a moment, but first, a little more background on Kepler. He became, within 2 months, the imperial mathematician. He got Tycho's place. Kepler had many interruptions to his work. He too had to cast horoscopes. He had court duties. His wife and several of his children died, much to his distress. He decided to remarry, and it took him several years to choose a new wife. But in a modern sense, what Kepler did was he had 11 possible brides. There should have been 10 on his list, but there were 11 because there was a mother-daughter pair who were competing with each other. And he essentially made the ancient equivalent of a spreadsheet, and he wrote down their attributes, what was good about them, and he scored them and calculated who would be the best wife. But in the end, he married the one he liked best, and that marriage was even happier than his first and lasted the rest of his life. During the time he was doing the calculations on Tycho's data, his mother was accused of being a witch back in Germany. This was because Tycho's brother was having a financial dispute with somebody, and they decided to get at him by accusing Ma Kepler of being a witch. She was thrown in prison for 14 months, put in a dungeon, threatened with torture. The torturers explained how they would strip the skin off of the bottom of her feet, pull her joints out on the rack, and encouraged her to avoid this torture by admitting being a witch, which she refused to do. Kepler then took a great deal of time off to defend her against the Inquisition in court, and he was successful at that. One of the court scribes at one point recorded the defendant, this is Ma Kepler, is represented, alas, by her son, the imperial mathematician Johannes Kepler. And that alas thrown in rather shows the court was not very unbiased. So Kepler got his mother off an accusation of being a witch. That was not normal. Most of the time, witches were convicted and executed. So Kepler worked on Tycho's data for about 18 years. After 8 years, he wrote his first book, The New Astronomy, or Commentaries on the Motion of Mars, in which he published his first 2 laws. And then 10 years later, he published his second book, Harmony of the Worlds, in which he published his third law. So during those nearly 2 decades, Kepler was calculating, but I don't want you to imagine him sitting at his desk calculating. Remember, he had no calculator, he had no computer. Everything was done by hand with a pen on paper. He didn't sit at his desk doing that because his hemorrhoids were so bad he couldn't sit. He was in such pain that he stood all of that time at a higher desk in order to do his calculations. And what he discovered are Kepler's laws, which I want to show you now. Kepler's first law is that each planet moves about the sun on an orbit which is an ellipse with the sun at one focus. And here's a diagram of an ellipse. An ellipse is a rather squashed circle. It has 2 focuses or foci. The sun sits at one, there's nothing at the other one, and the planet orbits the sun on an ellipse. Why did it take Kepler 8 years to discover that when the ellipse had been known since 600 BC? And the answer to that is the Greek astronomer, the Greek mathematician, who in 600 BC first wrote down the mathematics for the ellipse, was named Apollonius. And Apollonius is given credit for the discovery of the mathematics of the ellipse, but he's also the person who invented what we now call the dogma, the rule that because heaven must be perfect, everything in the heavens must be perfect and they must move on perfect paths. And the only perfect path is a circle. And so Apollonius declared everything in the sky must move on circles. And Kepler said if the motion was only an ellipse, if it were as simple as that, Apollonius would have known this 2,000 years ago. He eventually had to throw away all the other choices and discovered that the motion is an ellipse. Now, there's a long axis to the ellipse we call the major axis, And half of that major axis is what we call the semi-major axis. We characterize that with the letter A. And when I tell you the distance from the Earth to the Sun, the astronomical unit, we mean the semi-major axis of the Earth's orbit about the Sun. Kepler's first law. Kepler's second law was that if you draw a line from the planet to the Sun and then let a certain amount of time go by, let's say 1 month, the area swept out by this line between the planet and the Sun is constant for any period of time equal to 1 month. Now, when the planet's farther from the Sun, it's moving more slowly. When it gets closer, it moves more quickly. And that's what Kepler discovered. The planet speeds up as it gets close to the Sun, slows down when it gets farther away, and this is the rule he discovered. We now know that that's what we call conservation of angular momentum. And when we're teaching astrophysics to first-year undergraduates in university, they can calculate that now from first principles. And then after 10 more years, Kepler discovered his all-important third law of motion. Here it is, as Kepler knew it. The period of a planet, as it goes around the Sun, measured in years, squared times itself, is equal to the semi-major axis, the distance of the planet from the Sun, measured in astronomical units, cubed, or times itself twice. So P times P equals A times A times A, where that's in years and this is in astronomical units. That works for all the planets he knew: Mercury, Venus, Mars, Jupiter, and Saturn, and of course for the Earth, where both of these numbers are 1. We'll come to Isaac Newton next, but Newton discovered that Kepler didn't have that quite right. This is Newton's form of Kepler's third law, which says the masses matter. This is the mass of the Sun, the mass of the planet. The reason Kepler didn't notice that is the mass of the planet is so tiny compared to the Sun, it hardly matters. And the constant in the equation, so that the units can be universal, is just the number pi, 4 pi squared, over the universal gravitational constant. Kepler wanted, the reason it took him 10 years to discover this is he wanted the motions of the planets, the periods, to be in a harmonic series. And this musical notation is from his book. He believed in the music of the spheres, which arose with the Pythagoreans, again, hundreds of years BC. So for 2,000 years, the idea of the music of the spheres reverberated down the centuries and the millennia. And Kepler so believed in that he tried to fit the orbits of the planets, the periods around the Sun, to a harmonic series. And what made him perhaps the first great astrophysicist is that after a decade of trying to do that and failing, he threw away his cherished ideas, went back to first principles, and discovered his correct law of motion, Kepler's third law. This is the law by which we discover the masses of just about everything in the universe. When we tell you the masses of planets around other stars, the masses of stars orbiting each other, the masses of stars orbiting galaxies, and the mass of galaxies, from which we conclude galaxies are mostly made of dark matter and the universe is dark matter, all of those calculations of the masses in the universe, almost all of them, come from this equation, which is a form of what Kepler discovered. It's the reason why he's so important. Now, Kepler was having an idea that was kind of physics. He thought that there was a force in the Sun that kept the planets moving. Now, he didn't understand inertia. He thought that if nothing kept pushing the planets, they would coast to a stop, just as things here on the Earth, if you give them a push, coast to a stop, because he didn't know about friction. But he had this idea, there's a force in the Sun. His idea wasn't right, but the idea was forming, and physics was to grow from that. Now, Kepler died, as you'll see, in 1530. Isaac Newton was born 12 years later. Isaac Newton, some people might argue, was perhaps the smartest person who ever lived. I don't think that you can actually decide an argument like that, because how do you compare the intelligence of Isaac Newton with the intelligence of Beethoven or Michelangelo, or of somebody whose brain is working in some other incredibly, unbelievably human thing to do? But in terms of a physicist, Isaac Newton stands head and shoulders above just about everybody else. Some people might say Einstein is on the same level, but he was truly a phenomenon intellectually. He invented his 3 laws of motion. Those laws are that an object in motion will continue in motion unless a force acts upon it. It's the law of inertia. He invented calculus, which he needed to do his calculations. His second law is that force is equal to mass times acceleration. His third law is For every action, there's an equal and opposite reaction. And that's what we use for all of our space travel, to put satellites in orbit, rocketry. He invented the law of gravity, which is the force of gravity depends on a constant. That's the gravitational constant. It depends on how much mass each object has. There are two objects here. And it depends on how far apart they are squared. This is just the geometry of a sphere. So this is geometrical. He invented that law of gravity. He invented his laws of motion. He invented calculus. He didn't learn this from somebody. He invented it. And he calculated that if the planets are kept in motion around the sun by gravity, how should they move? And from that, he derived Kepler's laws of motion of the planets. And he knew he was right because Kepler had already discovered that from the observations. Newton did all that by the time he was in his early 20s. Now, he didn't publish for decades. That's the case. But he had actually done all these amazing discoveries here by the time he was in his early 20s. Phenomenal intellect. Now, I want to jump back a generation before Isaac Newton. I want to take you back now to Lancashire, where I worked for 19 years, where Andre and I met when he was 10 years at the University of Central Lancashire, because our institute at the University of Central Lancashire, we called the Jeremiah Horrox Institute. That's the institute that Andre worked in too. Jeremiah Horrox was born in 1618 in Toxteth, which is now simply part of Liverpool. It's only about a mile and a half from the docks in Liverpool. But in 1618, it was out of town. Liverpool was not very big. In fact, surprisingly, in 1618, Preston had a larger population than Liverpool did. So Jeremiah Horrox was born into a family that was reasonably well off, but not wealthy, in 1618. And by the 1630s, when he was in his early teens, he went to Cambridge. But his family did not have the money to pay for that. He had to work his way through university. He was a sizer, which meant that he had to do odd jobs in order to support himself. And he probably worked as a tutor to a wealthy young boy, helping him with his studies and learning as he went. He never did graduate because you had to pay for graduation, so he never did get a Cambridge degree. But it's recognized now that Jeremiah Horrox was the master of the new Keplerian astronomy in Europe at an age of 15. He proved that the moon moves in an elliptical orbit and follows Kepler's laws. He recalculated Kepler's tables. Now, Kepler had calculated that Venus would pass in front of the sun in 1631, but Kepler didn't live to see that. We don't think anybody watched it. Horrox recalculated Kepler's tables and discovered that Kepler had made a mistake, and Venus passes in front of the sun twice in 8 years, and there was another transit of Venus coming up in 1639. He predicted that, and then he observed it. Now, this is a Victorian painting you're looking at. It's in the Astley Museum in Chorley in Lancashire, and it shows anachronistically Horrox as some sort of pilgrim, which didn't exist in his time, looking with a telescope that didn't exist in his time, but he did have a telescope of a projection of the sun onto a screen. You can't look directly at the sun. In November of 1639, watching the shadow of Venus as it passes across the face of the sun. He did do that. He had a pen friend named William Crabtree, who worked in Salford, a suburb of Manchester now. Crabtree was a milliner, and Crabtree also, from Horrox's calculations, observed the transit of Venus, November 1639. They were the first two people ever to do that, to see Venus pass in front of the sun. They planned to meet following the transit. Jeremiah Horrox finally saved enough money to be able to travel the 30 miles from Muchhool, where he was working, to Salford, where William Crabtree was, and the day before he was to go to meet Crabtree, he dropped dead. We have no idea what happened to him. He wasn't known in his lifetime. He was just short of 23 years old. We have no idea what his genius might have led to had he led a normal life. We do know that he made phenomenal discoveries and had big impact in his short 22 years. His observations of the transit of Venus, 24th of November, 1639, were made from this house. It's called Carr House. It's in Muchhool, Lancashire, about 8 miles south-southwest of Preston, where Andre used to work and I used to work at the University of Central Lancashire. The family who owns the house gave us permission to come to the house on the day of the transit. Now, I organized an international meeting of astronomers. Over 100 astronomers came to Preston to talk about fundamental science, much of which was kicked off by Horrox's discoveries at the time of the transit. The day of the transit, we took the day off. The transit lasts 6 hours. We started by watching from the Alston Observatory. We were in luck. It was clear for us. We saw the start of the transit. We had a nice breakfast at Alston Hall next to the observatory. And then we came down here, courtesy of the owners of the house, to look out of the window here from which Horrox watched that first transit in 1639. There were other people present that day. There were crowds. Patrick Moore was there with the BBC filming live, school groups. It was a fantastic day, and we actually saw the transit. Here's a real picture of Venus in front of the sun. The transits of the 17th century were the one that Kepler predicted and nobody saw. The 1639 transit, which was watched by Horrox and Crabtree. Then there weren't to be two more transits until you can see here in the 1760s and then the 1800s. 2004 is the one I watched from Lancashire. The 2012 transit was watched primarily from Hawaii and the Pacific. And if you missed all those, there's your next chance. Good luck to you if you'd like to wait for that. How does transit work? Well, the transits of Venus are very important. And the reasons for their importance come from science that was discovered back just after the time of Jeremiah Horrocks. The English Civil War put the stop to a lot of things. With the beheading of Charles I, there were a group of men. Ladies, I'm sorry, it was only men then. This has changed dramatically nowadays. It is no longer. And with the Restoration in 1660, with Charles II put back on the throne, the Royal Society was formed. It's arguably still the greatest of scientific societies around the world. American would, of course, not agree with that. They would say their National Academy of Sciences is the greatest science society. And as we'll see, the French would not agree with that either. The Royal Society was founded by the likes of Isaac Newton, of Edmund Halley, and of a man who was the civilian professor of astronomy at Oxford University until he was 29 years old, and then he changed careers, decided to do something else with himself. It's the reason I'm showing you St. Paul's Cathedral here in London. We're looking across the Millennium Bridge, because this other founder of the Royal Society, who started off as professor of astronomy at Oxford, changed his careers, and when he died, he was buried in the crypt in St. Paul's, and his son put up a plaque in his honor. If I can get my plaque to come up, folks, bear with me. It's in Latin, and if you read here, it says, Lector, si monumentum requiris circumspice. Reader, if you seek a monument, look around you, because he was Christopher Wren. And of course, we know him for his work in architecture, and particularly in this case, for rebuilding St. Paul's. So the Royal Society was founded, and it was looking for major scientific problems to work on. Well, if the English are to have a Royal Society, so are the French. So in 1666, under Louis XIV, with his first minister, Colbert, no money was spared. The Académie Royale de Sciences was formed, and with that, it was decided to build an observatory. Colbert was told to spend whatever was needed. There's the Observatoire Royal in Paris now, as it looks. I've had many meetings myself in the Salle de Réunion, the council hall in that building with its spectacularly beautiful painted roof. It's not very far from the Jardin de Luxembourg. Well, for those of you who know Paris, you've probably been to the Jardin de Luxembourg. And this observatory was famous in its time too. The French set off to hire the best minds in Europe to be the scientists there, again with no expense spared. And so they were hiring scientists the way a football club nowadays has no expense spared to hire the best football players. They tried to give a very big salary to Isaac Newton to get him to come. He refused. He stayed in England, but great salaries, fantastic French food, wonderful facilities. And the Observatoire Royal was then the premier royal observatory in the world. Well, of course, the English are not going to accept that, so we had to have a royal observatory too. And the Royal Navy was the funder of the Royal Greenwich Observatory. Almost all of you will have visited that on your trips to London. You've been to Flamsteed House, Flamsteed being the first astronomer royal. But the Royal Greenwich Observatory was not built on an unlimited budget. It was built out of used bricks from a building that had been there prior to it. The wood came from an old gate from the Tower of London. And it had one astronomer royal and one assistant. That poor assistant was paid only £24 per year. And even then, in 1675, that wasn't very much money. Problem that they were set to solve at that time, the greatest problem in astronomy, was how to determine longitude at sea. Both for the French and for the English, for the other royal societies of Europe, this is what they wanted to discover. And many of you will have read or know about the lovely little book called Longitude by Dava Sobel. I'd recommend that to you if you haven't read it. The astronomers thought that they would determine longitude at sea by using the phases of the moon or by using the moons of Jupiter. In the end, after great battles, it was won by clocks that were made, which could go on a ship that was pitching and rolling at sea. Obviously, a pendulum clock can't do that. Think of a grandfather clock on a ship rolling at sea. The pendulum's going to bang into things and come to a stop. John Harrison invented the marine chronometers that would work at sea and allowed sailors to determine their longitude at sea. Latitude's easy in the northern hemisphere. You just measure the height of Polaris above the horizon, but longitude was the problem. Now, when I was a counselor for the Royal Astronomical Society, when I was vice president, the council of the society, of course, are the trustees of the charity. It is a charity, and they are legally responsible for the valuable things that the society owns. And some of the things that the Royal Astronomical Society own are some of the Harrison clocks. They're on permanent loan, semi-permanent loan to the Maritime Museum in Greenwich. A few years ago, there was a lovely exhibition in which they were displayed at the Maritime Museum. But as a counselor of the Royal Astronomical Society, if something happens to those, the counselors hold legal responsibility. In the library in Burlington House in London, we hold a copy of a first edition of Copernicus's De Revolutionibus. On the open market, that book would go for more than £1 million. There are many other valuable manuscripts like that, which are held in humidity-controlled, temperature-controlled, locked, library and controlled room at Burlington House. So Harrison won the battle for determining longitude. So what would be the next big scientific challenge for these observatories in the next century? And then comes Edmund Halley. Halley, you know from the name, from Halley's Comet. Halley, if you look carefully on this painting of him, was the civilian professor of geometry at Oxford. He was the secretary of the Royal Society. He was a great assistant to Isaac Newton. And Halley realized that by watching Venus pass in front of the sun, we could determine the distance to the sun. He put that idea in motion, even though he knew he wouldn't live until the time of the next transit. Here's an actual movie of, if I can get it to run for you folks, hang on. I may or may not get this to run. All right, my movie's not going. It would show you slowly Venus passing in front of the sun. And here's how the method works. From two different places on the Earth, you look at Venus as it passes across the sun. You'll see it pass across different parts of the sun. And by measuring how long it takes, you can get the latitude on the sun. You can therefore measure this angle right there. Because these two lines cross each other, that's the angle on the other side. And you now, if you've measured the distance between your two measuring positions, you've got a baseline, you've got an isosceles triangle, you've measured the distance to Venus. And of course, as I told you earlier, because of Copernicus, we know the relative distance of Venus to the sun, 72%. You've just discovered the distance to the sun. This was the great challenge for observers in the 1700s. The Royal Society, the Royal Navy sent expeditions out. Many other societies did too. And so in 1760, for the 1761 transit, Charles, who was an assistant astronomer at the Royal Greenwich Observatory, was hired to lead an expedition to Bencoolen in Sumatra. to observe the transit of Venus. He needed an assistant, and all astronomers were taken up by that time. There weren't that many in Europe. So he hired a surveyor named Jeremiah, who purportedly was born in a coal mine in County Durham. And Charles and Jeremiah boarded His Majesty's ship, the Seahorse. It was a gunship, in December of 1760, and sailed out of Southampton down the Solent, excuse me, folks, past the Isle of Wight, thinking they would not be home for perhaps more than a year. Well, as it turns out, they were home 3 hours later with 11 dead and 37 wounded. This was during the 7 Years' War, and they had sailed into the guns of a much bigger frigate, Le Grand, a French ship, which blew them out of the water. They limped back to Southampton, and Charles immediately sent a letter to the Royal Society saying, "We will not proceed thither. Let the consequence be what it will." The Royal Society immediately sent a letter back from London saying their refusal to proceed after having so publicly and notoriously engaged in it would be a reproach to the nation in general, to the Royal Society in particular, and more especially and fatally to themselves. It could not fail to bring an indelible scandal upon their character and probably end in their utter ruin. The Royal Society didn't stop with that. They also noted that it would, with the most inflexible resentment, prosecute them with the utmost severity of the law. Charles and Jeremiah at that point saw things in a different light. When the Seahorse was repaired in February of 1761, they got back on board and they sailed for Bencoolen, this time with a better naval escort, this time without the French ships blowing them out of the water. They went down the coast of Africa and they put in at Cape Town, as all ships did at that time, to reprovision fresh water, fresh food, fresh produce. There's a picture of Cape Town, a time exposure. You can see the beautiful stars as they move in a time exposure about the South Pole, of which there is no South Polar star. This being the southern hemisphere, the stars go clockwise around the pole, the opposite of what you see in the northern hemisphere around Polaris. And there's the cable car on top of Table Mountain, 1,000 meters high, and there's beautiful Cape Town. They got to Cape Town and discovered that the French had taken Sumatra. They couldn't continue. They were actually delighted, and they set up to observe the transit of Venus in Cape Town. Just as a little aside here, I'd like to just show you, if you look at the front of Table Mountain here, there's the lower cable station, and a cable car carries people on a cable up about 700 meters vertically to that upper cable station. Well, my wife and I met in 1983, and for our first date, we walked up this pathway, up this grass, and then we climbed these rocks and around the side to the top of Table Mountain. Given that was 1983, you can see that was a very successful first date up the front face of Table Mountain. Charles and Jeremiah watched the transit from the parade in Cape Town, and they observed it completely successfully. For their observations to be used, they had to survey their position very precisely, and they were so good at that that they measured the position of the observatory in Cape Town to such high precision that the Royal Navy knew the distance from the Royal Observatory at Greenwich to the Royal Observatory in Cape Town better than they knew the distance from Greenwich to Paris. Well, with that fame, in the colonies in North America, two of the colonies had been having a legal battle. The Penn family of the colony of Pennsylvania and Lord Baltimore, who was the head of the family that ran the colony of Maryland, came to an agreement about where the boundary between their two colonies should be in 1763, and they wanted the most famous surveyors in the British Empire to come survey it. So Charles and Jeremiah went to North America, and for 4 years they surveyed a boundary running due west, straight line due west, to divide the two states of Pennsylvania and Maryland. When they were finished, the boundary was named after them. They were Charles Mason and Jeremiah Dixon. Boundaries called the Mason-Dixon line. It divided north from south. It divided free state from slave state. The entire south of the U.S. came to be called Dixie after Jeremiah Dixon. And if any of you like Dixieland jazz, the next time you're in New Orleans listening to some Dixieland jazz, think about Dixie, think about Jeremiah Dixon, and it'll bring your thoughts back to this talk and the transits of Venus. And although the transits were successful in measuring the distance to the sun, astronomers are always wanting more precision. And so in 1769, it was decided to send more expeditions out to observe the transit. This time, the transit was on the other side of the world, only just being discovered by Europeans from a European point of view. And so the Royal Navy took an old colliery ship that had just been transporting coal and refitted it as a Royal Navy ship. Here's a painting showing it to you in Whitby Harbour in Yorkshire. But they couldn't get a Royal Navy captain to agree to take command of the ship. It was going to sail around the world to take astronomers to some island nobody had ever heard of to watch Venus pass in front of the sun. And the Royal Navy captains knew there was no career-making prospect in being captain of that ship, and they just refused to command. So the Royal Navy then found a young lieutenant who had been making a name for himself surveying in Canada on the St. Lawrence River and in Newfoundland, and he agreed to take command of the ship. He was not captain when he took command, but he was shortly thereafter promoted to captain, and it is as captain we've known him ever since. This ship is the Endeavour. His name was James Cook, and it was the greatest sailing expedition of all time. Talk about a career-making move. They sailed to Tahiti, where the transit was watched from Point Venus. It's only 11 kilometers up the coast. For those of you who've been to Papeete, if you're standing on the shore there looking across to the island of Maria, off to your right, just 11 kilometers away, you could walk it in 3 hours, is Point Venus, where the astronomer Green and his assistants successfully observed the transit of Venus in 1769. Now, I don't want you to think that all of these expeditions went well, and so I want to digress and just tell you a little bit about poor man, a Frenchman who tried to observe the transits of Venus. You'll see here his name, Guillaume Joseph Hyacinthe Jean-Baptiste Le Gentil de la Galacier. I'm going to call him Le Gentil for short. You'll see here his book, Voyage dans la mer de l'Inde, Voyages on the Indian Ocean, by order of the king. And there's his drawing from the book of what a transit of Venus should look like, but poor Le Gentil. He sailed out during the 7 Years' War to what was then called Ile-de-France. We now call it Mauritius, fantastic holiday resort, but back then it was a hot, humid island with no culture. He missed Paris, and he surveyed the Indian Ocean. He endured the mosquitoes, and he made plans to observe the transit from Pondicherry in India, but 7 Years' War, the English took Pondicherry from the French. And so he wasn't able to do that. He actually got caught out at sea, and he observed the transit. It was clear he saw the whole thing, but there's no way he could pinpoint his position, and his observations were useless. Because there was a war on, he didn't think it was worthwhile trying to make his way back to France, so he stayed for another 8 years, surveying quite successfully Madagascar, parts of the Indian Ocean, the islands, the Seychelles. And then come the next transit in 1769, he went to Manila to try to observe it from there. But there were rumbles of more war in Europe. The Spanish ruler in Manila thought that he was a spy and threw him in prison. Eventually, letters from the French Academy got him out of prison, where he sailed to Pondicherry, now back in French hands with the ending of the 7 Years' War, built an observatory there, was well treated by the local ruler, was all set up for the transit. Conditions were perfect the night before, and he woke up the morning of the transit to howling wind, pouring rain, incredible storm. The storm lasted almost exactly 6 hours, and just as the transit ended, the clouds parted and the sun came out, and he had got nothing. Dejectedly, he went back to Ile-de-France. He packed up to go home. Took him a long time to get a ride home, but eventually he caught a ride home on a Spanish warship, which, as it was sailing up the west coast of Africa, had heard that a new war was starting, and it actually captured and boarded an English ship coming down the coast. The English captain asked what all the fuss was about. The Spanish captain thought a war was starting. English captain said, everything has been settled, there's no problem. And the Spanish captain said, well, you can't fool me, that's the oldest trick in the book. But the English captain had some newspapers he had brought with him from England, which showed that what he was saying was true. And so the two sides exchanged gifts, port and such, and sherry from the Spanish to the English, and potatoes, I think, from the English to the Spanish. The ship sailed on, and Le Gentil finally got off in Spain in Cadiz and said, I'm not sailing anywhere anymore. And he walked across the Pyrenees, walked home to Paris, to discover he had been declared dead. His entire state had been inherited by his heirs, and he had lost his seat on the Royal Academy. Well, the Royal Academy kindly provided a special new seat for him for the rest of his life. Through the courts, he recovered some of his wealth. He married, had some children, and so far as we know, he lived rather happily his last 20 years, but he never again did astronomy. Now, the Frenchman Joseph Jérôme Lefrançois de Lalande then solved the problem of the distance to the sun, and here's the answer. He found 153 million kilometers. Here's the modern value, pretty good. All of a sudden, we knew how far away the sun is, and we then knew that the sun shone with a brilliance of 3.8 times 10 to the 26 watts. If you don't like it in that notation, folks, then that's 384 septillion watts, if that helps you. It was phenomenally bright, and nobody knew where the brightness came from. Well, the next century, parallax was finally discovered. The wiggling of the stars as the Earth orbits the sun, and the first measurement of parallax was done in the 1830s. And with that, we had finally discovered how far away the stars were. Alpha Centauri, 4.3 light years away. It's as bright as the sun. And so then the question was, what powers the stars? Lord Kelvin in Glasgow, Helmholtz in Germany, both did a calculation we call the Kelvin-Helmholtz time. Our undergraduates can do this. If the sun and the stars were powered by gravity, which was thought to be the great source of energy, think yourself, if you pick up something like a glass and drop it on the ground, it smashes from the gravitational energy that it gains in falling. This is a calculation, gravitational constant, mass of the sun, radius of the sun, and how bright it is. They calculated the sun could shine for 20 million years with gravity powering it. Chemical energy couldn't power it even that long. And so what powers the stars? At the end of the 19th century, no one knew the answer to that. But then in 1905, Albert Einstein published a special theory of relativity, and he gave us, I think, the world's most famous equation. Energy and mass are equivalent. E equals mc squared. Energy equals mass times the speed of light squared. 15 years later, the great British astrophysicist, professor from Cambridge, Arthur Stanley Eddington, suggested the stars are powered by hydrogen fusion. Eddington had a problem, though. He thought that the composition of the sun and the stars was pretty similar to that of the Earth, and that they didn't have very much hydrogen. And his calculation showed there really might not be enough hydrogen to power the stars. Well, that problem was solved in 1925. Cecilia Payne was a young English woman who wanted to do her PhD in astronomy, but couldn't do it at Cambridge or Oxford. They did not admit women. She went to Harvard College Observatory to do her PhD work. I've said here it's a Harvard PhD thesis, but in fact, Radcliffe College gave her PhD because Harvard itself also didn't give PhDs to women at that time. Radcliffe College did that. Otto Struve, who was one of the great astronomers of the 20th century, said something that most of the rest of us agree with, undoubtedly the most brilliant PhD thesis ever written in astronomy. Cecilia showed the sun is mostly made of hydrogen, and by inference, the universe is mostly made of hydrogen. And with that, by the end of the 1930s, we knew how hydrogen powered the sun. The details were worked out by Hans Bethe and his group. You'll see he lived almost 100 years, escaped Germany, 1933, with the rise of the Nazis, worked at the University of Manchester for a while, but then Cornell University in the US poached him, and it was at Cornell that he developed our understanding of the proton-proton cycle, where 4 protons, 4 hydrogen atoms, are fused to 1 helium nucleus. And with that, we then understood the power of the sun comes from the sun fusing 600 billion tons of hydrogen to helium every second. We understood that in 1939. By 1950s, we knew how to do it. We knew how to fuse 100 kilograms of hydrogen to only 99.3 kilograms of helium. 700 kilograms of mass disappears. E equals mc squared. And we produce these absolutely horrendous, devastating weapons, hydrogen bombs. There's a picture of the explosion over Bikini in 1954. These weapons have got the explosive power of 1 million tons of TNT. There are thousands of them in existence. I don't normally bring politics into my talk, but I will right now. Your Prime Minister, I'm English too, so I guess mine too, has recently decided that the UK will lift its limit on the number of atomic weapons it holds and is going to actually acquire more. I can't imagine greater stupidity. Off with the politics. These weapons were invented. We understood the power of the stars, but at the moment we've only used them for absolutely horrific purposes. We really do need to decommission all of these weapons so they never get used in anger. Here is a movie of the explosion of the biggest hydrogen bomb test ever, the Tsar bomb in 1961, exploded off northern Siberia by the Russians with a power of 50 million tons of TNT. We don't want to do this. The reason I'm showing it to you is I'm showing you that we do understand how the stars get their power. And what we're trying to do now is to do that under controlled circumstances with hydrogen fusion power stations. The International Thermonuclear Experimental Reactor is being built in Copernicus, France. Even with Brexit, we remain, the UK, part of it. It has a weight, there you'll see, 23,000 tons. This thing is gigantic. It will raise the temperature of hydrogen in its toroidal-shaped core here, which is a complete vacuum. Keeping the hydrogen in place with magnetic fields, it'll raise the temperature of the hydrogen to 150 million degrees so that you get hydrogen fusion. Of course, 150 million degrees would vaporize the power plant, so the magnetic field keeps the hydrogen from touching the edges of the power plant. And this power plant will put out 500 megawatts of power. This is the ultimate source of energy for humanity. We will have green energy, but in terms of vast amounts of energy, we will use hydrogen power in this century. This is an engineering problem which we are now conquering. And with the advent of hydrogen power, we will be using nuclear fusion to produce power. We'll be able to desalinate seawater for fresh drinking water. If we choose to, we can water the deserts for our crops. Let's hope that we're wise enough not to cover the planet with 100 billion people instead of only our current 8 billion. That's a political decision, but we will have vast amounts of energy at our beckon. It will have some radioactive waste, but that radioactive waste, if it's contained, will be safe in 100 years. The radioactive waste we produce with fission power plants presently, like Sellafield, will still kill you 1 million years from now. That's a much worse problem. So this is a relatively safe way to produce power with little radioactive waste, which only needs to be controlled and contained for about a century before it will be safe to let it back into the environment. It's being built. There it is under construction. You can see it rising, and that will come online over the coming decade or so. In the US, they have the National Ignition Facility, which is using petawatt lasers to do the same job. These are, a petawatt is 1,000 million watts, and these lasers are fired simultaneously onto little pellets of hydrogen, heating them to the millions of degrees necessary for hydrogen fusion. We're trying to do the same thing in the UK. Private company is now building a tokamak. This is like the International Thermonuclear Experimental Reactor, but smaller. A tokamak reactor here in the UK. Here's a Nature article from 2019. Here's the company's website right here from last week. Tokamak Energy is on track to be the first private company to achieve 100 million degree plasma temperature, paving the way to commercial fusion energy. There's the future. There's the big payoff. I've taken you on a trip this evening, ladies and gentlemen, from 400 years ago with Copernicus, who was just trying to figure out how the planets move, through Tycho, Kepler, Jeremiah Horrox, Captain Cook, Cecilia Payne, Albert Einstein, Arthur Stanley Eddington, and many other people in a story of pure blue skies research where nobody could see it was coming, to the biggest payoff of all time, the control of hydrogen fusion and almost unlimited energy for human use. Thanks for your attention this evening. If you'd like to read more about that, here are some places for further reading. We will now take questions, and we need to bring Andre back here to share the stage with me. And there he is.
Thank you very much, Don, for fascinating talk. There are various comments coming in a live chat of YouTube from David Glean. Fascinating, thank you. David Royal, Sean Shields, very enjoyable, thank you. So we have some time for some questions. So what I'll do, there are some questions arrived during talk in the Padlet, which I'll look on my left, and I watch if people put questions in a live chat. One was from Corey Shirt, who asked during a session, when will be next transit of Venus?
Oh, that came up, Corey, that came up very quickly during the talk. There were a whole list of numbers there. The answer is 2117. And so with developments in medical science, maybe you'll get to see it.
Right, and then there is a kind of related, so to say, question in Padlet. Why were transits of Venus so important? And also kind of second arrived, did they see atmosphere of Venus during those transits?
The answer to the first question is the transits were important because they allowed us to determine the distance to the sun, and that then let us know how powerful the sun is. From that, we leapfrogged to learn the distance to the stars, and we discovered what the stars are. Your question, did they discover an atmosphere of Venus? And the answer is yes. Very famous Russian physicist named Lomonosov. How's my pronunciation, Andre? Where's the
almost right, Lomonosov.
Lomonosov.
Which just means, as a typical for Russians, someone who breaks nose.
Anyhow, yes, the atmosphere of Venus was detected.
Thank you. It's a question about those Harrison's clocks. There was a question, how many of Harrison's clocks survived?
That's a good question. I don't know the answer. I don't even remember now how many he made, but it was only a few. He had some prototypes, which were quite small. In fact, if I hold my hands up in front of my face, the Harrison clocks that I remember that the Royal Astronomical Society owns are about this size. I don't know how many of the ones that eventually went to sea built on his pattern survived. Let me trust that if you and I both go look on the internet later, maybe we can search out the answer to that. Thank you for the question.
I now read from Neil Taylor a comment or question. Transit of Mercury are more frequent but harder to observe. Historically, were these transits attempted to determine?
Transits of Mercury happen 13 times per century. And the transit of Venus, if you've got a filter to protect your eyes, you can see it with your naked eye. Venus is big enough that you can see the spot moving across the sun without a telescope. Mercury, you might prefer to have a small telescope, but you wouldn't need a very big one. And because they happen 13 times per century, well, you've got a good, I don't know when the next one is, but it'll be coming soon. And you may have a chance to see that. If you're on the right side of the Earth, if over the couple of hours it takes to happen, it's happening on the other side of the Earth and it's night where you are, you either have to travel or wait another few years for the next one.
Thank you.
Just see here, Andre, there was a famous story by the science fiction author Arthur Clarke, and some of you may have read some of Arthur Clarke's stories. He liked to put science in. It's called Transit of Earth, and it's about an astronaut on Mars whose mission has failed and he's dying. He's not going to make it home, but as he's dying, he sees Earth transit the sun as seen from Mars. And that idea was given to Arthur Clarke, of course, by the transits of Venus, which he knew about.
It's a beautiful novel, yeah. I see Matthew Arnott is asking, how long do we estimate we will be able to have controllable, usable fusion power, and what could speed up this research?
Oh, Matthew, I think your question is how long until we will have it? And
Yeah.
well, let me give you a definitive answer to that. When I was a student, the answer to that was 40 years. And the answer today, I think, is 40 years. The UK company is hoping to get in on that sooner. I think that the experimental reactor in France is hoping to be producing more energy than it consumes on a time scale of 1 or 2 decades. But when this will be widespread for all of humanity, I don't know the answer to that, but let me put it in perspective. If you look at Andre now on your screen, behind him stands Lincoln Cathedral. The people who decided to build Lincoln Cathedral knew that they would not see it completed. It was going to take more than a century. It was going to take lifetimes, but they trusted it would happen. And so is the case with hydrogen fusion. It's an engineering problem. We will solve it. It will happen. Will it happen in 10 years, 40 years, 3 generations, 5 generations? I don't know, but the future will come. It will happen. Just as you can see behind Andre right there, Lincoln Cathedral happened.
Thank you, Don. I see Matthew Arnott also put a comment with several applauses. Thank you so much. Watch it with my 14-year-old son who loves his math, space, and wants to study astrophysics at university. I think it's a good choice, isn't it?
I think it's a good choice too, and he's welcome in lots of places. In fact, he's looking at a man who might like to have him come study astrophysics with him.
I now look at
Andre. I'm retired. Sorry.
I'm looking now on the Padlet. There was some more technical sort of questions. How Kepler did calculations without calculus being invented yet?
Kepler was having to calculate trigonometric relationships. What he had to do was take Tycho's observation of altitude and azimuth. Now, let me put those technical terms in perspective. Walk outside, look at a star in the sky, measure the angle between the ground and the star. Find the point to the north, and then measure the angle from the north around to the star. So those are the 2 angles. How far around from north? How high in the sky? He then had to do trigonometry to calculate where that object would be in the sky with respect to the sun. And that was a whole lot of trigonometry. He would have used tables for that, and he would have been doing equations with his pen or his pencil and a piece of paper, and it was exceedingly time-consuming and probably very, very boring, and you had to be exceedingly careful not to make mistakes and probably double-check all your work. It's the reason it took him 2 decades.
Yes, very, very strong motivation, kind of, and love for science. I now see question again about hydrogen fusion by Andy Charlton. Great lecture, thank you. I have a question. How much hydrogen would be needed to produce enough power to run a country, and if this amount is available?
All right, that's a calculation we need to do. How much power does it take to run a country? Can somebody tell me that? I don't know how much power it takes to run a country. Give me a number.
Yeah.
All right, just a moment. I've got my calculator out here. There are 4.2 times 10 to the 9th joules in the explosive power of a ton of TNT. And, oh, actually, do you know, I do know the answer to that. We humans produce, I know that from another lecture I give, we produce about 10 to the 21 joules per year of energy. And so if I put that number in, 10 to the 21 joules, and 1 kilogram of hydrogen produces 4 times 10 to the 9, we would need, I've just got about 250 billion kilograms, or 250 million tons of hydrogen. And, water weighs a ton per cubic meter. All right, the answer is still a lot.
Yeah, I think as we know how this reaction work now, so there were.
But I forgot the number of seconds. I was doing seconds. Hang on, the 3 times 10 to the 7 seconds in a year. Just a minute. Oh no. Now we're getting down there. 8 tons of hydrogen. Okay, only 8 tons of hydrogen.
Right.
The answer I gave you was per second, not per year. Now that I've got it for year, we only need 8 tons. Easy peasy.
All right. So there are quite various questions. Given the limitations of observational equipment and knowledge back then, and I presume in history, it's Sean Chills asking, what do you hope to find and prove with the better equipment and knowledge we have now?
You mean what are the big discoveries still to be made? And perhaps, what good are they? Right, there are many answers to that question. Biggest puzzles today in astrophysics, what is dark matter? Does dark matter even exist? We have got another solution of the problem of dark matter, but that requires a different law of gravity we don't know. Is there a different law of gravity? Or is the universe really mostly dark matter and dark energy, and what is it? And if we can discover what it is, can we use it? I don't know the answer to any of those questions, so there's a direction to go. Big Bang. All of you probably wonder that. We astronomers will tell you the universe started in a Big Bang 13.6 billion years ago, and you're going to ask me, well, what was there before the Big Bang? And I'm going to tell you time started then. The word before isn't meaningful, and you're not happy with that. I'll let you puzzle about that. I don't know the answer. Let's come much more down to Earth. I work on the Transiting Exoplanet Survey satellite. I do something called astroseismology, but the satellite, along with its predecessor Kepler, has now discovered 5,000 planets around other stars. We're looking for planets like the Earth orbiting other stars, planets that have got rocky surfaces and water on their surfaces, and we're building giant new telescopes. The European Extremely Large Telescope, €1 billion, some of it coming out of your tax money in pounds. We're building giant telescopes, James Webb Space Telescope, so we can look at those planets away from the glare of their stars and look to see if their atmospheres look like they show there's life on that planet. To answer that question, are we alone? Is this the only planet in the universe that's got life? Are we the only intelligent beings? I don't know if that's useful, but it's really interesting. And those giant telescopes, one of the big answers they're after are, what are those planets like around the other stars? We found them now. We just want a close-up look, and we need bigger telescopes. And then those telescopes are going to probe back to the beginning of time, to the formation of the first stars, to find out more about how the universe originated. Where do we come from? Those are the most fundamental questions anybody can ask. That's what those big telescopes are doing. If the farmer asked me, what good is that? Well, go look for that medical advance and hang around for 400 years. Maybe we'll find out.
I see there are more questions arriving both in live chat and Padlet. However, our time reserved for lecture is running to the end, and I also tell that people who came to listen to our virtual talk quite from various places. There is Dominic Camarere, who writes a very interesting thank you from Albany in your talk. So we have a greater community with us, and we do hope that next lecture you don't give here in person in Lincoln, and some people can come in person, and we would have more time to discuss. So with that, I would like to thank Don for absolutely fascinating talk and this 5th Robert Grosseteste Lecture in astrophysics. I'd like to thank our audience who stayed with us, And also, as it's common now for YouTube, if you like the talk, don't hesitate to push a thumb up under the YouTube, and you can also subscribe to this channel when some other videos will arrive. And with that, I would like to wish good evening to everyone, and to Don as well, because he's still in a similar time kind of difference with Britain, not too far. Thank you very much, everyone.
Thank you from me too. I'm glad you came.